this next speaker really loves retro games. And he's the author of the second best Pandas book ever written. Please welcome Wes.
Hi, everyone. I'm happy to be here. I think this is there a missing year in the middle of COVID? I think maybe this is like year 8 or year 9 for me in a row. So it's been a long time. I was looking back at old videos, old slides to see how much I've aged. So this talk is a little bit of a retrospective on projects that I've been working on in my career, things I've been thinking about. So I wanted to share a little bit of that with you. Maybe you'll find it insightful or interesting. First, I wanted just something light. Is anyone playing this game right now? Like, okay, it's a pretty good game, right? Like, okay. So most of you know me from the Pandas project, but in recent years, I've been focused in on the Apache Arrow project and projects in and around Arrow, like Parquet. There's another Python project called Ibis that we've been investing in significantly in the last few years that you kind of think about as dplyr for Python. But I definitely want to call out that these open source projects don't happen without a great deal of support, and so I'm very grateful for all of the support that I've had over the years from many of these companies and some that aren't listed. Definitely, I think it's great to see RStudio Posit expand into building tools and infrastructure to support Python developers as well, so that we can build better software and tools for teams that use multiple programming languages. So without the support of these companies, a lot of my open source projects would not have been possible. And I also want to give a shout out to the Pandas community. I think a lot of people credit me for creating Pandas, which is true, but I haven't really been deeply involved in Pandas development for about 10 years. So the project is 15 years old. For the last 10 years, I've been focused on other projects, and in the meantime, there's grown a large community of open source developers around the world, thousands of contributors that have made this project possible and have made it possible for Python to be a good language for data science. But when I started out, things were a little bit different. This is a picture of me from my very first conference talk at PyCon 2010 in Atlanta. And at that time, what I was really concerned with was the opportunity that Python had to be a first-class language for statistics and data science. And so I was working to find collaborators and figure out how we can make that possible. And so the first paper that I wrote about this was, so we didn't even call it data science back then, it was statistical computing. So this is from SciPy 2010. And I'm going to point out that it's a bit ironic that I am here at an R conference and Hadley Wickham is in Austin at SciPy. So we've Hadley still is not writing any Python code at all, but we've essentially traded places. But I think that's telling in a sense that it shows that over the years that we've had this really fruitful interchange of ideas between these communities. The Python community has obviously taken a lot of inspiration from the R community. I had used R before I got interested in building tools for Python. And you can see that at that time, this is a quote from the paper, and so I thought that there was a great opportunity to attract users to use Python for statistical applications, and that we could make Python a good language and ecosystem for doing data analysis. This was the moment on Twitter a little over 12 years ago when I decided to drop out of grad school and devote myself full-time to working on Python and Pandas. So at that time, I was really concerned with how do we get the Python community to work together to build good end-to-end solutions that people can use, that are accessible, and people can get things done. So I wrote this blog post also nearly 12 years ago, so July 2021. And the basic message of this was there's all these projects and they don't work well together, and this fragmentation is killing us. And I think that, what the I think what we can learn from the Python community can learn from the R community. I think that, R has been really good at building these like unified approaches to solving problems, like the impact of the tidyverse on making R productive for data science is really impressive. And I think to an extent, like in the Python ecosystem, we still have a lot of fragmentation at the software level, and users are often left with like, wow, I've got this huge smorgasbord of packages to choose from. I just want to get something done. And at times, and this is the nature of open source software, it can be difficult to know which tools to use. And these days, there's multiple data frame libraries in Python, and so a lot of people are asking me like, Wes, like Pandas is cool, but like, should I really be using polars now? Or there's other alternatives as well. But at that time, 2011, 2012, I wrote my book, Python for Data Analysis. But these were tools for working with small data. So you might be dealing with somebody who is an Excel user, and they might be more productive writing code rather than using a spreadsheet. And so, when we were building these tools, we weren't really thinking about massive, really massive, big data sets. We were building tools to empower people to work on data that fits on a laptop. But at some point, I started working with larger data sets or building applications. We had, so Chang, one of the early Pandas developers, we had this startup DataPad. We started working on building a cloud application for analytics where we needed to have low latency and work with large data sets. And we started experiencing, the pain of scalability and performance in that environment. So I gave this talk 10 years ago that was subtitled 10 Things I Hate About Pandas. And so the things that, that had been about 5 years into the experience at that point. And so some of the things that we had learned, well, firstly, is that a lot of data analytics problems, data frame problems are very similar to database problems. And so taking the approaches and using the tools for numerical computing, basically what you would see in MATLAB or in projects like NumPy, and trying to solve these database problems led to this mismatch that created a lot of issues. But to build really high quality database systems is actually really difficult and requires specialized skills and know-how. In Python in particular, the absence of lazy evaluation was a major issue that it made it more difficult for us to optimize and plan queries and do various optimizations that would enable us to generate, to have more efficient libraries. And I think it's been cool to see how non-standard evaluation in R has been leveraged to do a lot of magic under the hood to enable applications to run faster. And we've taken advantage of that in Arrow land in building the Arrow R package and integrating with dplyr. But one of the main things which led to the next was the segue into the next part of projects that I worked on was the pain that we saw in plugging components together, composing one system with another, moving one data set from one environment to another, using multiple computing packages that have different data representations. And we saw that this was really dragging down the performance of our systems. So I think this was the first time I spoke at the New York R conference. It was in 2015. So I was thinking about this concept of if there was some way that we could decouple the data storage, data representation problem, and make that more modular, if we could make the execution engines, the computational systems that power the data frame libraries and the data systems more modular and reusable. And then that would enable people like me, people like Hadley, to just focus on building really high quality user interfaces that make people more productive. And so that specialization and decoupling would be really healthy for the ecosystem. So I predicted, 8 years ago that we might be there by 2025. So I'm happy to say we've made some progress. And so I'm going to talk a little bit about the ways in which we've made progress toward that goal. I don't know that we'll entirely be there by 2025, but we've made material progress in the last 8 years, which has been really exciting. But what's driven some of this change and why there's been this kind of collective awakening to the need to build next generation data systems is because hardware has evolved at a rapid pace in the last 10 years. Solid state drives, like storage devices, have become orders of magnitude faster. Memory, networking has become orders of magnitude faster. We have new types of computing chips, graphics processing units, which are enabling orders of magnitude more compute throughput for the same amount of power. So there's all of this pressure that's building up in the system space that's causing us to have to rethink the software layer on how we can leverage all of this rapid change and innovation in hardware performance. Oops. Okay. And so one thing that arose also around this time that I haven't really been involved with very much is general purpose parallel computing frameworks. So the ones that are most popular in Python are the Ray and Dask projects. And so what these projects enabled you to do was to take Python code that runs on one machine and build a computing graph that can be planned and executed with a scheduler on a cluster of machines. So you're taking your Python code that runs on your laptop and dividing up the problem into a bunch of small pieces and then running them on a cluster with one of these frameworks. The problem with this approach, and there was a paper also written in 2015, so I don't know if you're noticing a trend about like everybody thinking about this problem at the same time, is that one of the problem with general purpose parallel computing frameworks is that they give you scalability, but they introduce a lot of overhead that's associated with scaling out, and you introduce a lot of communication and latency associated with building distributed systems. So this was a group of researchers from Microsoft Research that wrote a paper where they examined distributed systems for solving big data problems and looking at how much overhead is introduced in order to achieve scalability. Now, it's worth pointing out that imperfect scalability, the ability to scale, is better than not being able to scale. And so you have a small data problem, and that you can work with that on a laptop. But if you have a big data problem, you need to figure out how to chop it into small pieces and run it on a cluster. Now, time has passed, and so the definition of what constitutes small data now, you can get servers in the cloud with 24 terabytes of RAM. And so, in a sense, like a terabyte of RAM, in a certain sense, could be considered small data when you can get a server that big. So worth keeping in mind. And perfect scalability, where going from a problem at size n versus n times 100, if you need to use a distributed system to solve that problem, you're not going to be able to have 100 machines and process 100 times as much data in the same amount of time. So you will pay in order to have scalability. So the finding from this paper was, the published work on big data systems have great scalability, but how much are the systems really improving performance as opposed to parallelizing the overheads that they introduce? And so there's this concept of the configuration that outperforms a single thread. And so the way I kind of synthesize all of this is that not only do we need to build systems for making distributed computing easier, but we also have to improve the performance and efficiency, not only of what we can do on a single machine, but also looking at how we connect machines together in a distributed system. So another quote that I like from this paper is, you can have a second computer once you've shown you know how to use the first one. So we've been attacking this problem kind of across multiple fronts and building some supporting technologies to make it more feasible to build practical real-world systems that have these more beneficial future-proof properties of a lot more efficient computing. So one of them is the Arrow project, which has brought a language-independent, universal, I call it like a memory fabric or a data fabric that enables us to connect hardware, programming languages, and systems and move data around and compute on it in different environments a great deal more efficiently. So also around the same time, this was in 2017, there was a group in the Netherlands, Mark Rosveld and Hannes Mulhuizen, who wrote about the difficulty in getting data out of database systems and how databases spend a lot of time converting data to an intermediate format to serve it to you. And these ended up being the folks who created DuckDB, which is another big part of the story of how things are changing in our modern times. But first, a small thing. One exciting thing that's happening more recently in the Arrow ecosystem is some of these offshoot projects to introduce and push down the Arrow data format directly into database systems and storage systems that serve and process data. And so one exciting thing that literally just happened in the last month or two, we've been working, collaborating with Snowflake for a number of months, is that we natively incorporated the Arrow database connectivity standard into part of Snowflake's database driver stack. And we believe that this will be a blueprint for how modern database drivers are built, enabling applications like Python and R that speak Arrow and have an Arrow-based data frame interface through libraries like dplyr and Ibis to execute much more efficiently on large quantities of data that are being exported from a data warehouse like Snowflake. So kind of the way I think about this is that, this is a quote from Paul Dix at Influx Data, is that when you use Arrow, your data becomes your API. So you don't need to think about converting your data into some intermediate interface with its own API so that applications can access it. So another key part of this story is this concept of modular programming interfaces. So an API that you use, but then under the hood, you have the choice of different backends that you can select to execute your queries or evaluate your data frame expression. So I would say that dplyr really pioneered this, and I took inspiration from dplyr in starting the Ibis project in 2015 to do the same kind of thing for Python. And so over the course of the last 7 or 8 years, we've been building lots of backends, and so now dplyr has backends for many different database systems, for Arrow, for DuckDB, and the same with Ibis. And so that enables you to write your code once and execute it on many different backends. Another thing I'm excited about is new programming languages for describing complex analytics on data. So one project I encourage you to check out is the Malloy project, which is the Looker team at Google created this new programming language. And it's the same kind of concept where you have this high-level interface for describing analytical queries, and depending on the database or the backend you're using, it compiles to the appropriate SQL dialect under the hood. Another big part of the story is this concept of modular or embeddable query engines, query processing systems. So the two big projects which are going on actively right now, one is DuckDB, which I know had a big impact in the R ecosystem in terms of working with very large out-of-core on-disk data sets with SQL, and you can use that through dplyr, or you can write SQL queries directly to DuckDB. Another project is Velox, which is being led by developers at Meta, who were initially motivated by accelerating PrestoDB with columnar query processing, but is since being integrated into a variety of different downstream open source systems. And all of this is open source. And so in the past, you had all this cutting edge analytic database processing, but it was all happening in commercial database systems. And so as an open source developer, you couldn't just pick up the core functionality from Redshift or from Vertica and integrate it into your open source library because it was all closed source. But now we have these open source libraries that can be deployed and integrated very easily into your open source applications. So in the future, I expect that it's very easy now to have high performance, cutting edge analytical SQL processing in basically any application. You can run it in the browser, compiled via WebAssembly. Like it's really amazing stuff. And none of this existed 8 years ago. I think another important trend, which is going to become more and more important over the next 10 years, is the trend of hardware heterogeneous computing. And so we've seen through projects like Rapids, led by developers at NVIDIA, that we can do efficient analytics and data frame processing on GPUs. And there's another new company, Modular, led by Chris Latner from the LLVM project, which is building a new programming language, Mojo, that's built on top of the MLIR compiler framework, which is facilitating hardware heterogeneous, we write code once, and you can compile it and run it on a variety of different hardware devices and get cutting edge performance. So last thing before I wrap up and they kick me off the stage, is to make it easier for all these disparate systems to talk to each other. We realized that we needed to create an intermediate representation, like a language for systems for data systems to talk to each other at a low level without having to get into the details of like different SQL dialects and all of that mess. And so we've been working on some folks, some of my colleagues at Voltron Data, as well as a variety of other companies, Sundeck and some others. We've been working on this new project, Substrate, which provides this intermediate representation, low-level kind of assembly language for data analytic queries. So it's a low-level project. Most R developers would never need to know about Substrate, but it's one of these glue projects that we think will simplify and make these systems work a lot better in the future. So we need to bend the cost curve to make scalability more affordable in these systems. There's a lot of projects that are going on right now to enable that. I'm very excited about where we are now and where we come from, and so we're doing all these things. And for the next generation of data science tools, I am very excited about ending the language wars by having the same quality, same performance, and the same underlying systems running under the hood in all of the languages that we use. And I think 8 years ago, when I was at the first New York R conference, I was talking about this, and it seemed like kind of a pipe dream at the time, but actually, like, it's happening. It's here. Like, it's a reality. And so I'm very, very excited. And that freedom that it gives developers and users to choose the language that makes most sense for their work, whether that's Python or R or something else, I think that's a good thing, and we should encourage more of that to happen. So thanks for listening, and I'll be around this afternoon, so look forward to chatting with you. Thank you.